Alright, so last time, what did we do last time? Last time we fixed one serious flaw with the world. You know, the world has icons and logos for everything. They've got a logo for love, they got a logo for peace, they've got a logo for happiness. Even the Jonas Brothers have a logo. So there's something wrong in the world where even the Jonas Brothers have a logo, but the fundamental theorem of calculus has no logo. So that was wrong with the world last time, but we took care of it. We now have a logo, this super integral, and what did we use it for? We used that to compute areas, and we said only your imagination can limit you. All you need is a little common sense, a little imagination. If you can imagine yourself cutting it up into something into many pieces that are infinitely small, and you can compute the dimension of each little one, you can add infinite many of them with great ease and elegance, like it's never been added before. They could be this way or they could be that way. There could be many different ways. Only your imagination can limit you. If you can imagine it, the swaggeress can add it gracefully. What we want to do today, we want to continue to find areas, and we want to exploit this idea that if you can imagine it, you can add it. And last time, all our imaginations were pretty standard. They weren't that imaginative per se. They were just rectangles, they're that way or this way. So today we want to shake it up a little bit and imagine even more different things. The common sense ideas from before still apply. Horizontal distances are difference of x's, except when they're really tiny, that's a dx. Vertical ones are difference of y's, except when they're really tiny. And we know how to compute the dimensions of those, base times height. Okay, just common sense. By the way, you should be cautious of other people who will try to attack your human dignity. A lot of books have actual formulas, and they tell you if you do this, do that, and they try to take away all the thinking and all the common sense from it. And that's why I do this, because I think this is really the very powerful way to look at it. So just be careful when you read other textbooks or other sources. They may be giving you cooked up formulas that really are not needed. All you need is common sense. Left minus right, top minus bottom. Alright, enough of that. Let's review real quickly. Let's go with something classic today. Something timeless. Something we already know the answer of. What's the, everybody's done this since junior high. The area of a circle is equal to pi r squared. In this case, if the radius is 4, then the area is equal to 16 pi. We already know the area, but today we want to continue to imagine different things and foster the creativity idea and the idea that you can do all this with just common sense. So here we're going to find this result using the super S. Okay. Here's one way to do it. One way to do it, which is not maybe the typical way, but that's why I like it, is to take a line here. Imagine a line from here to here, and imagine another line similar to that one, but this time it's going from here to there. And here's the game plan. I know that if I took the entire area here, this is 4 by 4. I know that area for the whole square here, everything in the square, that's 4 times 4, that's 16. But here's my game plan. I'm not going to find that. I'm going to know that that's 16, but to find out the area inside the circle, I'm going to just focus on this little area. See, if I can figure that area, suppose that area is whatever, blah, then this area right here will be the 1/4 of the circle area minus blah, and I'll be able to figure out the area of the circle. Okay, here I'll say it a different way. The entire square here is, I'll try this one. Take that, extend that, maybe copy it. Maybe extend this one, copy it. The entire thing is, whoa. The entire thing is 4 plus 4. That's 8. 8 times 8 is 64 square units. Alright, the entire thing The entire circle is, the entire square is 64. I'll find each of these little corners, I'll multiply by 4, and I subtract it, and I'll have the area of the circle. Capiche? Alright, talk is cheap, let's do it. So first I want to make this my boundary here. That's my boundary. Man, I wish I could make good straight lines. How about that one? Ooh, I'm good. You know you want this, skills, right? You know you want it. Alright, so here's the game plan. I'm going to find this little area right here, the one in the corner. Why? Because I can. I just want to do things differently. I want to celebrate the human dignity, that the part of it that contains creativity. Not the undignity where they tell you exactly what to do it and how to do it every single time like you can't think. That's what I hate. Okay, this is what I love. I love to be a free-thinking person. What if, here's a what if. What if I have a whole bunch of these, and, you know, they get smaller and smaller and smaller. I have a whole bunch of these and I add them all up, then I will have the area of this region. I'll multiply by 4, I'll subtract it from 64, and we'll be done. Huh? How about that? Let's do it. So all I gotta do is find the area of one little one, this little one, dA, that would be base times height. And I can already see that the base will be, what will the base be? Here's the height. What do we call that last time? What is it? It's a little dy, and the base will be difference of x's. So I'll call this x1, I'll call this x2, then the little area would be equal to x1 minus x2 times the height, which would be a dy. And I can take it a step further here. X1, what is x1? This was fixed to be 4. So x is equal to 4 for this whole thing. So that would be 4 minus, what's x2? Well, that x2 is determined by this line here. And that line is determined by x squared plus y squared is equal to 16. That's the standard unit equation for a circle. So my x squared would be 16 minus y squared. So x would be plus or minus the square root of 16 minus y squared. Notice I'm getting two of them, one for this part of the circle and the other one for the other part of the circle. Again, if my rectangles were going all the way to the other side, I would use the minus one, but they're stopping here at the positive one. So we'll go with this x right here, which is equal to the square root of 16 minus y squared. Okay? So this would be 4 minus the square root of 16 minus y squared times a dy. That's my little area. Now comes the power of summation. I'm going to add all these up, and I'm looking at my y's. My y's go from here all the way up to they start here at y equals 4. They stop at 0. From 0 to 4. Think about it. All these little y's. I have a bunch of these little rectangles starting at y is equal to 4 and stop at y is equal to, start at y equals 0, stop at y equals 4. Clear? So this is our integral. Let's get to it. That would be the integral. How would you do that? The integral of 4 minus the square root of 16 minus y squared dy going from 0 to 4. You can break that up into a couple integrals. First one's rather harmless, from 0 to 4. The other one is rather interesting. 0 to 4, the square root of 16 minus y squared dy. I'm going to go with some classic stuff. I'm going to do trig stuff. So I'm going to make y is equal to 4 cosine. No, I'm going to make y equals, cosine would work. Sine would also work. Sine theta. So that would force dy to be equal to 4 cosine theta d theta. And that would force y squared to be 16 sine squared theta. 16. If you can't change it, join it. That would put us at this spot right here using the dictionary. That would be the integral of 4 dy from 0 to 4 plus, or minus the integral from 0 to 4 of the square root of 16 minus 16 sine squared theta, and then the dy would be times a 4 cosine theta d theta. And that would be equal to the integral from 0 to 4 dy minus This becomes, I'm in the first quadrant, so everything's positive, so I can say this would be the square root of 16 cosine square. 16 cosine square, that would be the integral of 4 cosine theta times another 4 cosine d theta from 0 to 4. Oh yeah, this is exactly what you shouldn't do, because this is theta now, so these limits were okay. I'm glad I caught that. These limits were okay, 0 to 4, they were okay for y, but they're not okay for theta, so I'll deal with the theta later. Anyways, let's continue with this, shall we? So this becomes, I'll deal with my limits later. This becomes integral of 0, and I can even take care of this one right now. 4y going from 4 to 0, that part is easy. This one becomes 16 cosine squared theta d theta, and let's again, I can either change my limits to theta limits or change the integral when I'm done with it, change it back to y's. Let me go with the thetas here. If y is equal to 0, I take this and I plug it into here. If y is equal to 0, what would that make? Sorry, if y is equal to 4, what would that make theta? Well, I'd have to think something like this. I'd have to think 4 is equal to 4 sine theta. So therefore 1 is equal to sine theta. So therefore theta is equal to 90 degrees, or 90 plus 360, etc., etc. Because I'm in the first quadrant, my theta is moving from 0 to 90, so I'm going to go with 90. So this would be pi over 2. That's a good upper limit on theta. And the 0, I plug the 0 in here. So I have to solve 0 is equal to 4 sine theta. That would give me 0 degrees, or 0 radians. And there you go, I got theta limits on it now. That's perfect. And I will continue. So this becomes 4 times 4 minus 4 times 0. That's that part. Minus 16. Oh, this is the famous idea where you take out a half and you go 1 plus cosine 2 theta. It's a famous identity that reduces that power right there. From the identity sheet. Famous identity sheet. Alright, let's continue here. So this becomes, that just becomes 16 minus 8 integral from 0 to pi over 2 of 1 plus, alright, let's see if we can do that. What does that become? Can you just do it? I need some space here. This becomes 1, the integral of 1 is just theta, plus integral of cosine sine 2 theta. Of course I need a half, because if I made a use of where the u is 2 theta, my du would be a half, my d theta would be a half du. Yeah, if you're rusty on this, you got to go back and do like 1,000 of those. This has to be automatic. Anyways, your limit is going from pi over 2 to 0, and that would give you, what would that give you? That would give you 16 minus 8 times pi over 2 plus a half sine of pi, minus 0 minus a half sine of 0, for a grand total of, let's extend this page, for a grand total of 16 minus 8 times sine of pi is 0, 0, 0, 0, 0, pi over 2. Aha. So this becomes 16 minus 4 pi. Wow. 16 minus 4 pi. What in the world did we just do? Let's go back to here. We just found out that this area right here, this one is 16 minus 4 pi. That's this area. Right? And the whole thing must be 4 by 4, which is equal to, the whole thing must be 4 by 4, which is equal to 16. This is 16, and this is 16 minus 4 pi. This is 16, and this 16 minus 4 pi. That forces this area right here. That must be that this one is 4 pi. Just that part of the circle in the first quadrant. So that means this one is 4 pi. By the symmetry, if this one is 4 pi, this one is 4 pi. Therefore, the area of a circle is equal to 4 pi plus 4 plus 4 pi. That would be 16 pi, as expected. Told you. See why they pay me? Pretty nice, huh? Classic stuff, where you figure out the area of a circle using deep S, blue S, red S. I don't know. Pretty nice, huh? There's plenty more where that came from. To this problem, let's do it again, and this time let's do it using polar coordinates. That requires some more common sense and some more imagination. Okay, let me tell you. Common sense. This one goes back to high school or junior high. Whenever you remember when you were finding areas of circle, the whole circle you knew was the area was equal to pi r squared. But if you had a portion of it, say theta, then that's only a portion of the circle. The area for the sector would be theta over 2 pi. That's the portion of the circle that you have, times pi r squared. That's the entire circle. These two cancels, and you get this timeless idea that the area is equal to r squared over 2 times theta, where theta is given in radians. You remember this? Or sometimes they might have written it as theta over 2 times r squared. Same thing. Alright, move forward to the 17th century. What does that mean for itsy bitsy tiny little sectors, tiny little wedges? Well, the r is still the same. There's no difference there. The only difference is that the theta is not quite so big now. Is it? Now the theta is little bitty tiny theta. But so the tiny little area would be all identical. It would be r squared over 2 times a d theta. Okay? That's one way to look at it. Same shape, same area, same area. The only difference is instead of having a normal angle, you have an itsy bitsy tiny angle, which gives you itsy bitsy tiny area differential. Alright? Or here you could do it a different way. You could say, hey, area is equal to theta over, wait. You could do it a different way. You could say area is equal to r squared over 2 theta. That's from high school. And then you do the magical slapping of the d, slap a d on both sides, and you get that, what do you get? You get that the differential area. See, the r squared is a constant, and 2 is a constant, so they come out r squared over 2, and all you have is d times the differential of the theta, so you have the same statement, dA is equal to r squared over 2 d theta. There you go. Nothing but the power of common sense and a little 17th century magic that is the idea of calculus. Anyways, powerful idea. Let's flex the muscles here to find an area that we all know. So here's the imagination part. You imagine that you take the circle and you slice it up into little bitty tiny wedges. Not 1 or 2, no, maybe many wedges. I mean, there's a lot of wedges in there. You go like this, there's a wedge, there's a wedge, there's a wedge, there's a wedge, there's a wedge. Infinite many of these, okay? But let's just find the area of one of these and see how it goes. That little area would be equal to r squared over 2 times d theta, based on the discussion we just had like 20 seconds ago. And then we do the powerful, the uber idea of the 17th century. Add them all up. And now I observe my limits. See, theta is the index. Theta is the one that's changing. I need to know theta. What is theta going from and to? Theta is 0 degrees here. It's 90 degrees here. It's 180 degrees here. How many of these little wedges am I adding? I'm adding all these little wedges. Imagine all these wedges starting at 0 degrees and all the way around to 2 pi. Similar to what you measure the radians, similar to what you have done in polar coordinates in your trig class. It goes from 0 to 2 pi. Let me see if you guys cannot see that. Can you see that? You can see it. Alright, so let's see. What does that mean? Well, let me think. This is a constant for a circle, especially. Well, that defines a circle. That radius is constant. It's not changing anywhere, so it doesn't depend on theta. This r is a constant, as constant as they come, so I could pull it through the integral sign and I've left with this incredibly difficult integral of d theta. I'm just kidding, it's not incredibly difficult, it's incredibly simple, because all it is just theta evaluated from 2 pi to 0. But wait, it gets better. So then that becomes r squared over 2 times, you plug that in there, that's 2 pi minus a 0. And what does that give you for a grand total? Stop me if I'm lying, but the 2's cancel, the 0 goes. Isn't that just pi r squared? I told you. See why they pay me? Your imagination is the only limit, my friends. Anything that you can imagine, Super S can add. You can imagine a bunch of wedges, no problem. We can take care of that. If you can imagine rectangles, no problem. Anything that you can imagine, just about. We got the perfect medicine for it. Alright, let's do something that we haven't done before, something that we don't know. One where we both get to practice the idea and learn something new. Take this example from polar coordinates. How do you find, suppose you wanted to find, I'm sure you've asked yourself, how much area is in one of these petals for the famous, you know, these famous functions that you graphed in your trig class. You've asked yourself, right? Let's do it. So we already got all the ideas. All we need is, see, draw one of them. Boom, there's my little area. And you may say, if you're, some of you may be worried about this little region, saying, you know what, we're going to get an error there, man. That's not really good. It's not really a circle. You're right. This stuff was good for circles, but does it work for petals? Well, what you have to do is imagine the rest of the story here. This was going to be cut into infinite many little pieces, right? That were infinitely small. And what you have to address is whether or not cutting it up into many, many, many pieces that are infinitely small reduces the error or not. And let's look at the error. See, this error will be here, this error will be there, 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 and there. Even though there's a big gap there, when I make them thinner and thinner and thinner, that big gap gets smaller and smaller and smaller, right? So in fact, even though it looks like there's an error, there is, but that's when they're not infinitely small. When they get infinitely small, the error goes to 0. Even though we're using things that wedges from circles, and this is not a circle, it's still, it'll still get the job done. Right? Alright, so then let's do it. This little area, let's find that little area. The little area is equal to r squared over 2 times d theta, right? And that would be, and then I do the magical S, add them all up from where to where. Oh, by the way, in this case, r is not a constant. See, that's what makes this one different. Oh, I can't believe I'm doing this. What? Can you guys see that or not? You can see it? Oh my god, what a beginner. Come on now. There. See, this one's different than the other one because r is not a constant. R is changing. Every theta that I have, r is a different r. So I can't go on pulling this r to the side like I did before. That's what makes this one super interesting. It would be so super boring if it was the same thing. So now what? Well, r is given by this famous equation here for the petal with that many roses. And so I just go in and I substitute it in there. This will become r squared, which would be, I'm looking over here, it will become 9 times cosine square of 3 theta, which is actually a doable problem because remember we have powerful identities that help you reduce that square. We just used one like 2 seconds ago. So this is all but over. I got one more thing left to do here on this one. One more little tiny challenge is that's finding the limits on theta. Okay. So again, my theta will go from this theta 1, and it'll go I have a bunch of these little I have a bunch of these until I get to that part right there. I should have made that permanent. So these are my limits. My theta will go from here to here because that's where all the little wedges start, right? They start right here. And so I got to find out that angle and that angle. Well, how am I going to do that? Well, the key feature that defines these angles is that the r goes to 0 right at that point. Right at that point, the line it crosses the origin. That's what defines these angles. So I'm going to use that as my peg. I'm going to use that as my hint to solve for it. The hint here is that r is equal to 0, so I plug that in there. I say 0 must be equal to 3 cosine 3 theta. Well, I divide both sides by 3, so that would tell me that cosine 3 theta must be equal to 0. When does that happen? Well, here's a cosine graph. It'll happen when 3 theta is equal to 90 degrees, or it'll happen when it's equal to 270 degrees, or it'll happen a bunch of other times. Or it'll happen when it's negative 90 degrees, So I, etc., etc. So it happens a lot of times. A lot of times this line goes back and forth and it touches the origin many times. I just want this one and that one, which I can eyeball it. It roughly looks something like 30 or negative 30, which in fact is confirmed by solving the equations. Here are some of the places where it crosses the axis. 30 degrees, 270 divided by 3, negative 90 divided by 3, that would be negative 30. These are the ones I want, 30 and negative 30. Okay? And just to be sure, pick something in between like 0 and make sure you're in this pedal and not paddling backwards, because sometimes these R's go backwards. Or if you want the insect way to do it, you take your thetas and your R's and you go from negative 30, negative 20, negative 10 degrees, and you plug those in there and make sure that you're plotting these points right here. Okay. Having said that, I'll let you figure out the details. I've got my limits here: 30 degrees, pi over 6, negative to positive pi over 6, and now I'm good. This right here is duck soup. I'm not even going to do it because I'm way too sexy for the grunt work. But what a nice problem. You guys should take some time and do that one. I don't usually advertise anything on the site, but I think this is a good tool. Whenever you're way too sexy for the grunt work, you can use this excellent tool to help you check the grunt work. It's like a super calculator online. It's called Wolfram Alpha. I often use it to check my grunt work whenever I don't feel like doing grunt work. So you can put this in there. You're just typing the integral of 9 times cosine 3t. That's what I'm looking at over here. Integral we just had 9 times cosine 3t times cosine 3t. And you just type in from pi over 6, negative pi over 6 to pi over 6. Just type it in with words like you were talking to somebody. And this thing is kind of nice. Let's see if it'll get the job done. I bet it's going to be something like 3 pi over 2. There you go. I told you. 3 pi over 2. So this is an easy way to check your work once you've done. Let me zoom out of there. Once you zoom out of there, or once you do all your work here, it's an easy way to check that you did it right. Very nice tool. I recommend it. That one's got my approval for grunt work. All right. Let's see. Where were we? All right. So let's try one more. You guys want to do one more? One more, and then it'll be your turn to do on the homework. So this is another one where we shake things up a little bit. We don't go with regular X and Y and vertical ones or even wedges. We try something different. Actually, we do rectangles, but we try something different. This is famous. This is called parametric equations. Okay. Parametric equations. And in case this is new to you, what it means is that you have a parameter or another variable, like a t, and t describes the x in a separate function, and t describes the y in a separate function. And if you've never done this, you should take some time right about now, maybe pause the video, and understand what this means. Here's the easiest way to understand parametric equations. You make a little chart just like you would x's and y's, and instead of picking values for x or y, you pick values for t's. T is equal to 0, 1, 2, 3, 4, etc. Or in this case, if you look at C and you look at T and see they're inside the cosine or sine function, you might want to make them degrees, 10 degrees, 20 degrees, 30 degrees, 40 degrees, etc., or radians, whatever you want. I'll do the first one for us. If T is equal to 0, cosine 0 is 1, so that becomes 3. Sine of 0 is 0, so that becomes 0. So the first point right here would be at x equals 3, 1, 2, 3, and y is equal to 0. Check. And then the next one, maybe I'll do 90 degrees. If x is 90 degrees, if t is 90 degrees, cosine of that would be 0, and this would be 1. 1 times 5 would be 5. So that would give you up 5. 1, 2, 3, 4, 5. And in between here, there's a bunch of little x's and y's, and you'd have to plot them to understand this. That's just 20 seconds. I don't want to do any more. You should plot these so you get a feel for it. What ends up happening is this is a super famous equation. This is an equation of an ellipse. Okay? And you can also see it this way. You can see it this way. You can play the similar game like this, converting. So you could say, hey, x over 3 is equal to cosine t. Y over 5 is equal to sine t. If I square this, I square that, I square that, I square this, I square that, I square that, I square both sides and I square both sides, and I add them together, I get that x squared over 9 plus y squared over 25 is equal to sine squared plus cosine squared, which is equal to 1. Well, another way to see that this is the equation of an ellipse. Anyways, that's sort of review. I don't want to dwell on that. What I want to do today is I want to flex the, if you can imagine it, you can add it muscles. That's what I want to do. I want to celebrate this guy right here, Joule from the 17th century. That's why I don't want to spend too much parametrizing, blah, blah, blah. Forget that. But everybody should know. Besides, haven't you ever wondered, if you have an ellipse that goes out like this, 3 and 5, haven't you ever wondered what's the area for the ellipse? Everybody knows areas for circles, pi, square, blah, blah, blah. What about areas for ellipse? They're just as oval. So let's do it. I'm going to do it right here. Here's the strategy I'm going to set up. I'm going to just focus on the first quadrant, because I know I got 4 of these, right? I'm going to find this little area and multiply by 4. Okay, that's the strategy. I'll find this one right here and then multiply it by 4, because I got 4 of them. And I'm going to do it with horizontal or vertical blocks. Well, wherever I feel like it, right? I'm the king. And so are you when you're doing the homework. Let's do it that way. And let's proceed. So, using nothing but common sense. Man, that's why I love this thing. You supply the common sense. The slaggeress supplies the deep ideas. To add them all up, infinite many of them that are infinitely small. Alright, talk is cheap. The little area would be base times height. This would be x1, this would be x2, this would be a difference of x's, x1 minus x2. The thickness would be a little tiny dy. So the little area would be equal to, I'm going to substitute things in there, x1. X1, I'm looking at here, my x is equal to 3 cosine t. Minus x2. Well, x2 is easy, man. x2 is 0. Minus 0 dy. Oh my goodness, where am I going to get dy from? Or from over here. I need t's. I don't want y's, man, or x's. I want t's. This is going to be a t integral. So I go over here and I say, alright, if y is equal to 5 sine t, what would that make my dy? I slap a d on that side and I slap a d on this side. And I would conclude that my dy is equal to 5 cosine t dt. Take that. You know you want this. You know you want this. So then I go over here, my dy. 5 cosine t dt. So my little area would be equal to 15 cosine squared t dt. Nice. Now I go with the magical Joule of the 17th century, Super S, coming to the rescue. And I'm looking at t's, man. T's. Where are my t's going from? So this was, again, you'd have to go back to when you plotted your points here. When t was equal to 0, you start off at 3, 0. That's this spot right here. That's what t is equal to 0. T was equal to pi over 4. T was equal to pi over 6. Da, 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 da. At this point, it was pi over 2. So you go back in your plot points to see which t's are you going from. And in this case, we're going from 0 to pi over 2. And we're in business. This would become 15. Alright, I could do it using Wolfram, but sometimes I do like to do a little bit of grunt work. Like a farmer who sometimes likes to dig his or her hands into the dirt and just be a part of it. Yeah, sometimes I like to do the grunt work. Cosine squared, I'm going to pull out a 2 there. That would make it, it's going to be a color fest. I'm just going to keep it white. That would make it 1 plus a cosine 2t dt. That would make it equal to 15 over 2 t plus sine of 2t 1/2 there, and I'm going from pi over 2 to 0. Can you dig it? But wait, there's more. I'm just kidding, there's not that much more. I plug things in there. 15 over 2 pi over 2 plus a half sine of pi minus 0 sine of 0, 0. Whoa, what does that equal to? 15 over 2. It's coming, it's coming, it's coming. And what is the area of an ellipse? This would become, this is 0, 0, 0. It's pi over 4. No. See, my mind is way faster than my hands. That becomes 15 pi over 4. Say what? Aha. So let's take a look at here. That means that this piece right here is 15 pi over 4. And so is that one, and so is that one, and so is that one. So altogether the area is equal to 15 pi over 4, giving you a grand total of 15 pi. You know you want this. That's, my friend, that's how you find area of ellipses. And you can generalize. Here's a generalization. For a circle, it's if this is r and that's r, well, r is all the way around, so the area is equal to r times pi, right? Pi r square. For an ellipse, here's the difference. If this is a and that's b, well, the area, it turns out to be almost like a square, a times b, but you multiply times pi. That, my friends, you can redo that problem with the 3 and the 5, replace it with a and b, and this is what you'll get. That, my friends, that's why you want this. You know you want this, right? Alright, that was fun. Peace.